So start off here, chapter 26.1, definition of capacitance. So basically a capacitor is two parallel plates connected to the opposite poles of a battery. So the capacitor is just the plates that are storing opposite charge. And so the picture of that, say you have a battery here, positive, negative terminals that are connected to these two plates. That one wire going here, one wire going there. So these positive charges going into this plate are going to attract, electrons. So the electrons are going to, come off as these protons are going towards the plate. So as these electrons are coming off, going in, say this direction towards this positive terminal, it's going to leave this plate here with a net positive charge because the electrons are going to be attracted to this positive terminal. And conversely, the protons are going to be attracted to this negative terminal. So the positive charges are going to go down this way, leaving this a net negative charge. So I should probably write that in a different color, just how I squeezed it in here. So we have the positive Q, and then we have negative Q here. And so you guys see that so far? So wire connected to negatives, attracts the protons. Positive, attracts the electrons, leaving this net positive and net negative. And so this capacitor is consisting of these two plates of opposite charge. It's just holding the charges in place as we keep this connection live, because there's going to still be this conduit of positive charges here and negative charges there. And so when they reach the same polarity as the battery, we can say that this is at a maximum capacitance. Capacitance is the capacity to hold charge, basically. Okay. So that's just keeping it real simple. Now, between these two charges, of course, we understand from our previous concepts that there's going to be a voltage difference, a difference in potential, positive potential, negative potential. So we have a voltage that's held. So this capacitor made up of these two oppositely charged plates will not have these charges go back and forth between the plates. Now we can disconnect one of the plates and then we'll have a discharge. The capacitor will then flash, or we'll have a conduction in between the plates. It's very similar to when you push the flash button on your camera. Just one example of that. You are releasing or discharging a capacitor, and the result of that is the flash that you see in the camera. There is a distance d in between these capacitor plates, and we'll be talking more about it. So that's our picture of the capacitor. And then next, there is a voltage between the plates. We know a lot about that now, from previous lectures. Delta V, voltage difference. So you can say V minus A, or final minus initial. That's our voltage difference. Now the thing about the capacitor is that depending on the size of the voltage, is going to be directly proportional to the amount of charge on each plate. So Q, whether it's positive or negative, is proportional to the voltage. Higher voltage, 9 to 12 to 30 volt battery, whatever, the greater the charge that's going to be on the plates, and the strength of the charge on the plates. So this is of course, a linear dependent. So these are the linearly dependent, aka directly proportional, right? And we kind of know what that looks like graphically. As the voltage increases, so does the charge at the same value. So like static friction, before the box starts to move, our pushing force is going to increase at the same rate as the static friction that's opposing us. So the box is staying in place. So the charges are staying in place. So Q delta V, and so there's going to be a steady increase of both. Now there is the slope of this, the relationship between these two quantities is the capacitance, okay? So if we take a slope between any of these 2 points, you know, no matter what the points are, the slope's going to be the same. That relationship is capacitance, C. So, and just going a little bit further, you know, in terms of our voltage and potential, we know voltage difference is going to be electric field multiplied by distance, in this case R, D, S, whatever the distance variable we want to use. And so we can, you know, reduce this down to a electric potential. And of course, the electric potential can be at any point between the capacitors from a particular charge. You know, just showing that relationship again. So it's voltage reducing to electric potential. So this is, again, electric potential difference, which is E dot ds, or E, you know, and we integrate that to become the distance R or D or whatever the distance variable we want to choose, electric potential difference. And this is just the electric potential. This is the electric potential at a point, just like potential energy at a point. PE equals mgh at that point. And delta PE would be the difference between 2 points. Same logic here. So electric potential. And now we move on. That's just a side note, really. So step 5, we can just say that the capacitance is the constant value, because this slope is constant. Constant value relating voltage and charge. And it's always positive. The slope is, it's just a number, it's a scalar. No negative capacitance. You know, we're increasing voltage as increased charge, increase the potential difference. So capacitance is the constant value relating voltage and charge, and it is always positive. Okay. So if we take the slope, that will be, you know, the m equals delta y of delta x. And I guess we can do the old school this. And so capacitance follows, by definition, delta q, or q over v, q over delta v, not delta q, because q is the magnitude. So there's no deltas. Positive, negative, it's the same value there. So q over delta v. So there's a slope relationship. Capacitance then is charge over voltage between those two plates of distance d and surface area a, and we'll be relating all that stuff in a bit.
Oh, Mr. Kelly, the net charge, right?
It's the total charge.
Yeah.
It's charge, whether it's positive or negative. It's not net. It's just Q.
Okay.
All right, and so then so let me just write this here. It's like this. This is the ratio of the magnitude of the charge on conductors to voltage. You can do absolute value, but it's not necessary. It's magnitude. By this point, we should understand magnitude is just a number, and it could be, you know, whatever. Ratio of the magnitude of charge on conductors, conductor plates to the voltage. So hopefully we now have a good idea of voltage. Now, voltage is not the same as current. Most people say, oh, you know, high voltage, but they're talking about one thing and meaning another. Voltage is just a storage. It's what exists. It's a potential difference. Current, we got to put a conduit, a wire, or some piece of metal to have those charges flow. And now we have current. And getting into that soon. So this is always positive. Capacitance, always positive as constants are. Generally. Okay, get rid of that in a moment. And capacitance is measured in what is known as farads after Michael Faraday. So 1 farad, F, equals 1 coulomb per volt, because this is measured in coulombs, this is volts. So that's a farad. Units of farads. Now we usually talk about microfarads or picofarads or nanofarads because like a coulomb, that's too much of capacitance because it's directly related to charge. So just like we were talking about charge in terms of micro and nano and pico coulombs, we do the same thing for farads. Because, you know, we usually don't see capacitors in increments of farads. Like you're gonna have like a 2 petafarad capacitor. Yeah, I mean, I guess if you want to risk the blowing up your building, you know, make a capacitor of that size. But we usually talk about micro and nano and picofarads. So 1 farad is very large. So we usually look at, you know, pico to microfarad, stuff like that. You'll see a lot of your problems and, oh, okay, this capacitor of 2 picofarads, 6 microfarads. Okay. So as I was saying earlier, so the negative terminal of your battery attracts protons or positive charges. And leaving the plate negative, you know, leaving plate at negative Q and then vice versa. You know, leaving it positive Q because electrons will be attracted to the positive terminal. So just vice versa. And the capacitance is maximized once the voltage difference between the plates are the same as the battery. Now you have equilibrium. Now you know there's no more flow, if you will. You know, it's all at the same potential. Which is why if you go, you know, if you're on a power line or you know, you're at a power line, a fence that is high voltage, and you jump on the fence, you better jump with your hands and feet landing at the same moment. And maybe even then, you know, you're risking it. But the point of that is you want to be at the same potential as your power source. in order so that you don't get electrocuted. Because if there's a difference anywhere, oh, I got a pathway, I'm going through your body, boom, done. Okay. We had a question. That will never happen? You mean you will never do it? No, if that's what
No, I mean, like, you can't coordinate it in order to
no,
like touch.
it's hard to do. Again, I'm
Yeah.
being
I mean, for humans at least.
I was being funny. All right, just making a quick example that
Yeah.
you need to be at the same potential as your power source. Yeah. Okay, so let's do an example, I guess, quickly. Or maybe, all right, we'll do a quick example. And then we'll go on to 26.2. Okay, so we have this problem. How much charge is on each plate of a 4 microfarad capacitor when connected to a 12-volt battery? 12-volt battery. So C equals Q over delta V. We just solved for Q in each case. So I say Q1 or QA is going to be C delta V. And then that'll just be 4 microfarads, or okay, times the 12 volts. And so we want to put everything in terms of the basic unit, the whole unit. So this is 4 microfarads becomes 4 times 10 to the minus 6 farads. Or we could leave it like this and report it as microcoulombs if we want, but usually charge measured in coulombs. So just, you know, we have a couple of choices. So we do a 4 times 10 to the minus 6 farads times 12 volts, and then becomes 4.8 times 10 to the minus 5 coulombs. Or we can say 48 microcoulombs. So move the decimal over 1 to the right. Just, oh, that would be minus 4. And then, yeah, we go to the left. Yeah, right. So we have 0.48 microcoulombs. Yeah. Just add when we move it to the left. So, or 0.48 microcoulombs. It doesn't matter, right? So, you know, we got to know when stuff is trivial, right? So, C delta V, and again, the same capacitor, it said, what is the charge? On a 1.5 volts. So we do 4.8 times 10 to the minus, my charge. Same capacitor, 4 times 10 to the minus 6 farads, multiply that by 1.5 volts, and then we get
6.0 times 10 to the negative 6.
Okay, so 1.5, yep, 6 times 10 to the minus 6 coulombs. 6 times 10 minus 6 coulombs, or 6 microcoulombs, you know, just whatever your choice. 6 microcoulombs. Okay, great. Moving on to 26.2. calculating capacitance. Now, let's say that we had a capacitor and we want to calculate the capacitance by this equation, C equals Q over delta V. And so let's say that we had, here's an example here. So let's say that we had a spherical conductor, something like this, and we know that the potential at the surface and the inside is going to be the same potential as we learned last time. And so let's say that this will be radius A, and it's going to have a potential related to its radius A. Then somewhere out here, some infinite distance away, the capacitance, or not the capacitance, but the electric potential at this point is going to be equal to 0 because R is going to go to infinity. So the voltage in this setup from the electric potential here, let's say that this is going to be, a known electric potential at A, and then at R goes to infinity, the potential is going to basically be 0. So if we then, put this into our electric potential equation, which we have V equals KQ over R, but in terms of electric potential difference, this V becomes delta V, and so this becomes KQ 1 over A minus 1 over infinity. And the reason why I'm having A being the final, because initially, let's say I'm bringing some charge in from infinity to this position A, as is the conventional case when we're trying to bring something in from infinity to some point other than infinity, and then we can, determine what the potential is at a point other than infinity. So this will be our final potential minus the initial potential. So this obviously is 0, and so our voltage, if we will, is going to be KQ over A for radius A. And this A, it could be any variable, call it R, D, S, whatever. It doesn't matter. That's basically R, radius R. So now we take this expression for some shell that has potential. This potential is going to be the same inside and at the surface, say outside. Of course, as we get to some distance far, far away, as we get to R goes to infinity, the potential is going to go to 0. So, but before infinity, this potential that is the same on the interior of the surface and at the surface is going to be the same as we learned last time for conductors in electrostatic equilibrium. That potential is then going to start to die off as we leave the surface. It's going to be like that 1 over R dependence that we saw. It's going to just dip. It's going to do something like that as R goes to infinity. So, okay, so at this point, we really don't have a voltage difference per se, but in terms of these two distances R, the voltage difference in that context would be KQ over A. So in this equation, C equals Q over delta V, let's say that this would be my capacitor made up of this surface, and this will be the other plate of the capacitor. It's not really physical, but we could idealize this as some sort of capacitor. What this is going to be at a potential is going to be 0, and this is going to be a potential V equals Q over A. So the voltage difference between this so-called capacitor is KQ over A. Now is that clear? Let's stop for that, because If we had, so for example, right, if we had a, like we said before, we had these two plates. Oh, we have a voltage difference. It's easy, you know, that's not at infinity. But pretend that this would be at infinity. The voltage difference would be given by this. Does that make sense?
Well, Mr. Kelly, I'm kind of
Yes.
messed up. The KQ over A is the one for the inside, right?
It's for the
For
entire,
only taking.
it's for the entire configuration. It is for the one on the inside, but in this example, we're making a capacitor between two regions of potential. And in the most
And the
extreme,
second region is zero. It tends to infinity, so it's zero, and we take delta V, and we get only the inside one, right?
basically, yes, that is.
Yeah. Okay.
So we're really just saying delta V is V, but context is everything. That delta V is, let's pretend like there's a plate way out at infinity. Well, as you said, and it's true, there is no potential here.
Mm-hmm.
And so the voltage difference between this plate and this plate way out here is basically going to be the electric potential of the plate by itself.
Okay.
Correct, yes. All right. That being said, mouthful, sort of. KQ over A. We now substitute into this equation. Let's see what we can get out of it. Someone's trying to call me. Okay. C equals Q over delta V. Now this becomes Q over KQ over A. And then we also know that K is 1 over 4 pi epsilon naught. We're just doing everything in terms of simplest terms. We're trying to get a new expression for capacitance in terms of these two plates at some distance from each other. K is 1 over 4 pi epsilon naught, and then this is 1 over K, so we make our substitutions here. This becomes A over KE, where KE or K is the Coulomb constant. Because I just cut out the middleman here, so this is going to be, you know, 1 over K is basically 4 pi epsilon naught, and this is Q over A. And so so I'm basically just going past this point, but these guys are going to cancel out, and this guy's going to flip up. So capacitance overall becomes 4 pi epsilon naught times A. So that's another way of expressing the capacitance of between two plates. Or in our example here, this would be the capacitance between an isolated sphere, where our next plate in this capacitor here is at infinity. And so we derive this equation for that particular configuration. It's just another example of capacitance. We're just playing around with this fundamental idea. Okay, I got my distance D. What if I put the D, what if I put one of the capacitors at infinity? What's going to happen? I get a capacitance that's of this function. Okay. Now, let's go to parallel plate capacitors. So I have two plates, charge Q, negative Q. Now each plate has a surface area, right? We can just kind of idealize it like something like this. this is the region in between distance D. Each of these plates has a surface area A. And so these plates don't just have a point charge. Of course, this is a special geometry. And as we remember from chapter 23, the charge on each plate would be given by the surface charge density relationship of Q over A. Because if it was linear, it would be Q over L. And if it's a volume, it would be rho over Q over V. So the electric field between these two plates, positive to negative, our convention, is going to be given as Q over epsilon naught. Well, it's not a point charge, it is a surface charge, so sigma over epsilon naught. And that just becomes Q over A, which sigma is over epsilon naught. Or written better, Q over epsilon naught times A. So this is a way of expressing the electric field between a capacitor where we have we have surface area for each of the plates. All right, I'm gonna hold up. I have weird smartboard stuff going on. 1 second. Okay, so again, we're just expressing the electric field between the capacitors. We've already looked at the capacitance. We know that there's a voltage. We know that there's charge of magnitude Q. What does the electric field look like for a surface area of charge? We can't just use Q over epsilon naught, or else that would be the electric field. We have to use sigma because those plates have area, right? You have to pay attention to the geometry. So assuming uniform, that is a constant electric field, the magnitude of the voltage delta V equals field times distance. We've seen that back in previous chapters. Delta V equals E times D, electric field times the distance between the plates. And we know now that the electric field between those plates is given by this. And so we can then substitute and say delta V is equal to QD over epsilon naught times A. That would be the voltage in between two parallel plate capacitors re-expressed. And the capacitance then, Q over delta V, is going to be, Q over all of this, QD over epsilon naught times A. And that just becomes epsilon naught A over D. So for two parallel plate capacitors of area A and distance D between them, epsilon naught is the free space between them, this constant of proportionality between the plates, called the permittivity of free space. That is your capacitance. The capacitance can be expressed Q over delta V if you have charge and voltage. Or if you have area and distance, you can express it in this way. And so again, if I remember right, permittivity of free space, 8.85 times 10 to the minus 12 Newton meter square per Coulomb square, but the units are important. So that's our free space constant. That's another, so this is equal to that. So as the distance decreases, the capacitance increases. So, I mean, that should make some sense to you because the charges between the plates are getting closer and closer. So now we're gonna have this region of, high capacitance, high charge, and because now those charges are getting closer to each other, and so we're gonna have Much larger capacity for discharging effect. As the plates are brought closer, the distance decreases, and vice versa. As a distance increases, the capacitance goes down, area shrinks, capacitance shrinks. So we can play around with the variables. Okay. I think do a couple of examples here. Can you take the derivative of the distance d? No, there's nothing, not that complicated. You just have to reduce it. Derivatives, you know, if only we're usually with rates of change, we're changing a variable with respect to something else, time or some other variable. No, not that complicated. All right. So example 26.1, we have a solid cylindrical conductor of radius A and charge Q is coaxial with a cylindrical shell of negligible thickness, radius B greater than A, and charge negative Q. So we have something that looks like this. You have a little shell inside, cylinder inside, and then, so this is like a coaxial, you know, cylinder, cylindrical shell with a cylinder inside. So this guy has charge Q, and this one has negative Q. This is radius A, and then this one would be, oops, radius B. Find the capacitance of this cylindrical capacitor if its length is L. Okay, so again, the capacitor, two oppositely charged plates. And so the first thing that we want to do in our capacitor logic here, we have the equation C equals Q over delta V. We want to get expressions for both of these guys, Q and delta V, or yeah, for both of them, because the cylinder on the inside has length L. And so we can't just use Q. We're going to have to use its linear charge density equivalent. And then we have to get an expression for the voltage between those two charge plates. So one cylinder on the inside and a cylindrical shell on the outside. So first is, let's find our voltage. And we know already that voltage is the negative integral from initial to final E dot ds. Now, there's an electric field in between the two, the positive charge on the inside and the negative charge on the outside. There's an electric field that exists. So what we can do is we can use Gauss's law to get the value of the electric field in between those two capacitor plates, if you will, capacitor plates. So first thing that we do in this at this point is, let's see, we know that by Gauss's law, we have the electric flux, which is electric field times area. is equal to Q over epsilon naught. Okay, one second. I want to take a brief look at this because we don't necessarily need to do this, but one second. All right. So yeah, I just want to expand on what they didn't show in the example. So yeah, I said before, you don't have to do this, but it's kind of necessary to do this. It's just that in the example, they waved over this part of the result, and I don't want to do that part. So anyway, as I said before, let me erase this part first. We have a, if we look at this cylinder from the top, we have a cylinder on the inside and then cylindrical shell that surrounds it. Now there's a Gaussian surface that exists between the cylinder and the shell, and it's going to be a spherical Gaussian surface. Well, actually, not spherical because it's not sphere here. It's going to be cylindrical Gaussian surface. And so we have to take the area of a cylinder with our flux equation to get an expression for the electric field, then put it into the integral for the voltage, get the voltage expression, and then we have our capacitance. So all this stuff is all right. It's going to make sense here. So cylindrical shell, surface, cylindrical surface. So we have radius A on the inside, and then we're going to go to some arbitrary Gaussian radius R, and here's our radius B that we already had. So A, B, and R. R is what is the most important thing, because what we're trying to do, the importance of this is we want to find the electric field through that surface, or at that radius. So that'll help us with this integral, and it'll help us get the capacitance. All right, so electric flux, E times A, which is equal to Q over epsilon naught. And we're surrounding the whole Q surface. But remember that not only is Q here, it has a length, L. So that Q becomes lambda times L, where lambda is Q over L. Okay, over epsilon naught. The area of a cylinder is going to be 2 pi RL equals lambda, well, L, capital L is the same, over epsilon naught. So this goes away. And then we get our electric field at radius R through it at that point is going to be lambda over 2 pi R epsilon naught. That's the part they waved over. Okay, so now take this electric field expression, delta V is equal to negative E dot ds. We just got our electric field expression, so that just becomes, from start to finish, we can just call that A to B. It's going to be lambda over 2 pi R epsilon naught times dr. dr ds. I'm just keeping the variables consistent. If I can call this S and ds, it doesn't really matter. So now I can make this a little bit simpler, this 2 pi R business down there. So I know already that K is 1 over 4 pi epsilon naught. So then 2K would be 1 over 2 pi epsilon naught. So I'm just getting an expression for this, for 2 pi epsilon naught in terms of K. If I multiply this by 2, this becomes 2, and this is 1/4, 1/2, or 2/4, 1/2. And so now my integral becomes negative 2K lambda from A to B dr over R. And Jeremy will recognize this as a natural log. So anytime you have an integral, integrand expression of dr or d some variable over the variable, that's a natural log as a result. So we have 2K lambda natural log R from A to B. And so now we can evaluate this all the way out. 2K lambda natural log. So you go B minus A, final minus initial. And then natural log rules, entire natural log, when it's a subtraction, reduces to a division, the equivalent expression here. The equivalent expression there. So 2K lambda natural log of B divided by A. That's my voltage. Almost there. So now we were trying to find the capacitance. We go to the next page. So before I move along, I mean, please ask me questions. Did any part of that confuse you?
Oh, yeah,
I
Mr.
have a
Kelly.
question.
Yeah.
Okay.
All right, I'll go ahead. Why does it read ln b minus a, and then it turns into b over a?
Yeah, I had the same question.
Natural log rule. Natural log rule from your trig classes. They didn't teach you that? No, I'm just playing. Yeah, that's just a rule of natural logs. Identity, if you will.
I think it's different. It's written as like ln b minus ln a, making ln b over a. I think that's how it would work.
Well, yeah, I just didn't expand it out that way, yeah. But it's going to be multiplied by both, yep. I just didn't write that. So LNB minus LNA, yep. Or this.
Oh, yeah, I got it. It's
Because it's
similar
going to be,
to.
okay.
Oh, yeah, okay, go on. Sorry.
It's going to be multiplied by both natural log B minus natural log A, but you're basically right. I just didn't write it out that way. Okay, so, and because at this point, it is rather trivial. Do I need to write it out that way, or do I mean, we understand that natural log is going to be multiplied by both B and A, and it becomes B divided by A. Yeah. So then capacitance becomes Q over delta V, and then that becomes Q over that expression for delta V to K lambda natural log B over A. Then I know that my lambda is going to be Q over L. So Q divided by 2K Q over L natural log B over A. And that just becomes L over 2K natural log B over A. Now that was a mess, mouthful, but good problem. Incorporates Gauss's law, voltage, capacitance, integration. And that is my capacitance between a concentric cylinder with a cylindrical shell. In that configuration. Now, you get different geometries, you're going to get different capacitance expressions. as we see in the next example, but I'm going to skip over that one for the sake of time. So if you didn't see that, Edward, what we were just talking about, this guy.
Oh no, I saw it. I saw it.
Yeah, natural log B minus natural log.
Yeah, I know. It's like the regular log. I just had forgotten it.
Yeah, it's again. Sometimes you'll have to remember those old rules. Yep. Going on. Yeah. I think I will. Yeah, I'm gonna do capacitor combos and hopefully energy and be done. Okay, so section 26.3, capacitor combinations. Okay, now we're going to get into basic circuits here. And in a circuit, we're going to represent our circuit components by different symbols. So our capacitor will be like this. A battery will generally be like this for positive and negative terminal. This one having higher potential and negative, lower or zero potential. Resistors are going to look something like that. So those would be resistors, capacitors, batteries, and that's what we're going to be dealing with mostly until we get to about chapter 30, 31, somewhere in there. We'll get into inductors. You know, like the symbol for that would be something like this, and so on. So when we draw our circuits, we have to keep these symbols in mind so we can represent them properly. Switches, open and close switches. So we have something like looks like this. This will be an open switch. And this will be closed. You know, if we have a node here, just to indicate that this flap came down. Yeah. So now if we draw a circuit with capacitors that are next to each other or parallel to each other, the ones that are next to each other, we call them series capacitors. And of course, the ones parallel capacitors. So if I have a circuit that starts, you know, I have my battery connected to everything right here. So this will be my positive and negative terminal. And this will represent a wire, you know, connecting one capacitor to another capacitor. And then I'm going to come down to this parallel set of capacitors. And then for the sake of simplicity, let's come all the way back to my battery. So this is a closed circuit. This would be capacitor 1, capacitor 2, and so let's say this is 3, 4. So these capacitors are in series, and these capacitors are in parallel. Closed circuit. As soon as the battery is switched on, or we connect our battery to these capacitors, again, negative charges come to the positive terminal, and then this is going to be left with a positive charge here. And so this will be negative, this will be positive, this will be negative. So as these positive charges build up, positive charges here leaving this negative, positive, and then same thing goes here, but this happens simultaneously as soon as you connect everything together. So the charge on each of these capacitors here will be the same because they're connected to the same battery. So as we, but then the parallel case we'll talk about in a second. It's not quite the same. So for series capacitors, the charge is the same. And for parallel capacitors, we'll see that the voltage is the same because the voltage is going to be a difference between these 2 points, VA and VB. So they both are in between both of those 2 points. So the voltage difference for capacitors 3 and 4 will be the same, whereas the charges will be different. So we'll get into that. So let's say that we're looking at the entire circuit. Let's say that this would be point A, this is B, C, D, E, this is point F. So this will be, the nodes go like this. We're just, designating those points. And that'll be H. So the voltage from A to H is going to consist of the voltage from B to C plus the voltage from D to E. And those are your series capacitors. And then this is going to be plus the voltage from F to G. So like I said, these are series capacitors. The voltage for both of those. They have the same charge, but different voltage. And the reason why the voltage is different is because these 2 distances are different. Let's say that this is 1, 2, 3, and this is, not difference, but difference in quantity, because these are 2 different points, 2 different sets of points. So the voltage will be different for those 2 sets of points. So that's what we have for series capacitors. Same Q connected to the same battery, but the voltage is different because they don't occupy the same 2 points. So voltage will be different. Whereas the parallel capacitors, they share the same voltage points, F to G, but the charges will be different. The charges have 2 different pathways to flow.
Mr. Kelly.
Yeah.
When you say then they don't occupy the same point, you mean that there's a distance between them, right?
There's a distance between them, but they have 2 different distances. The B and C, B to C is not the same as D to E.
Oh, okay. They depend on the functionality, right? How they want to.
They're just at 2 different positions.
Oh, the positions. Okay.
Because voltage is between, 1 point to the next. They don't have the same 2 points.
Oh, okay.
So Q1 equals Q2 for series capacitors. But since capacitance Q over delta V, then delta V1, or from B to C, that would be Q over C1. And delta V2 will be Q over C2. So if we wanted to create one capacitor to do the same job as those 2 capacitors, C1 and C2, we would form what is called an equivalent capacitor. We call CEQ for equivalent, and that would be equal to the reciprocal sum of C1 and C2, because these two Qs are the same. So we make them unity, or we don't have to worry about them because they're the same. So in terms of the capacitance, the total capacitance or the equivalent capacitance for C1 and C2 would be the sum of both of those capacitances, 1 over C1 plus 1 over C2. For series capacitors. So this would be, if you have capacitors next to each other, this will be the equation for the series. All right, that's gone on too long there, but I'll leave that back. And so now, if we were going to solve it out for just equivalent capacitance instead of 1 over equivalent capacitance, the common denominator, we could do that. 1 over CQ, EQ, C2 plus C1, C2, C1. Again, it's just common denominator stuff. And then CEQ would be C2, C1 over C2 plus C1. If you wanted to make an easier expression for the equivalent capacitance of 2 series capacitors, it would be equal to this expression. Instead of doing 1 over, then putting common denominator and all that, so you can just go right here for any 2 capacitors. Now, for the parallel case, parallel capacitors, as I mentioned, C3 and C4 share the same voltage. So delta V3 equals delta V4. Are you guys seeing what I mean by that? Do you understand why that is? That both of those capacitors have the same voltage because they're between the same 2 points of voltage drop. They occupy, so both of these capacitors are in between F and G, so they have the same delta V. Whereas these delta V's are different. 2 different points, same 2 points for the same voltage, whatever that is. And you add all these voltages up, it's going to say if this is 6, let's say this is 3, this is 2, and this is 1. Total of 6 volts for the entire circuit, because it's like a conservation of charge, conservation of energy even, for the entire circuit. There's not going to be any part of the circuit that's going to be a greater potential than the battery, or vice versa. We're conserving charge all the way throughout. I mean, we're going to ignore any type of field effects or heating and all that good stuff. So we're conserving our system of its charge. So between those 2 capacitors, voltage is the same, but there's different charge for each. There's basically a different pathway for the charges to flow. So they don't have the same charge. They're not connected by the same wire, so they're gonna have different charge on each of those capacitors in parallel. So it's just vice versa. You have the same charge for series capacitors, different voltages, and parallel, same voltage, different charge. So the total charge between those capacitors, Q3 and Q4, so that's going to be the sum. Both of those charges are different, so the total is going to be the sum of the 2. And since capacitor total is Q3 over delta V, delta V3, and Q4 over delta V4, and we know that those are the same, the voltages are the same. So the capacitance, the equivalent capacitance for parallel capacitors would be in terms of 3 and 4, it's going to be C equal to C3 plus C4. So when you have two capacitors in parallel, 2 or more, you just add up the capacitances to get the equivalent capacitance. And again, equivalent capacitance is basically saying what one capacitor will do the same job as those two. What's the equivalent? In parallel, well, you can just add up the capacitors, the capacitances, and then that'll give you the one capacitor capacitance that will do the same job as those two in parallel. So like in vice versa for in series, this equation will give you the one capacitor that would do the same job as those two capacitors in series. Any questions on that? So some combinations. So I want to go through energy in a capacitor, and that'll be our last bit. And then we can do some examples as we close off. We'll come back to these capacitor combinations. But does everybody see that for the parallel for both cases? Any issues there?
Mr. Kelly.
Yeah.
I've been thinking about the first case that the C when you divided the C when you multiply the C2 by C1 divided by C2 plus C1. Just because the distances are different there, you have to divide them, or it doesn't depend on it. Because in this case, you said that they are parallel, and you just added them.
Your question is, I don't know what your question is. Okay, 26.4, we're talking about energy stored in a charged capacitor. Energy stored, charge, and a capacitor, 2 plates, right? Okay, scenario. So we're gonna just be explicit here. I'm gonna connect the capacitor to a battery. We did at the beginning. The capacitor builds up positive Q and negative Q through attraction to each terminal on each plate. Over time, as the charge builds up, so remember Q, now plates, it's big surface charge density. We can call it Q and negative Q for the sake of simplicity argument. But each of those plates has little DQs to make up their total positive Q and negative Q. So it's little pieces that are being built up. And so that becomes important in a bit. So the charge builds up each little piece. So the plate has little DQs all over the place that add up to the surface charge density sigma, which is Q over A. The charge builds up each DQ to become Q, technically Q over A. You know, just being simple here, or negative Q. So as that happens, the work in the system And it's going to go back to our previous understanding of what work is in terms of voltage. The work in the system and thus the work to move a charge is given by dW equals dQ delta V. From back in chapter 25, the beginning of 25, we know that the total work is Q delta V, but we're talking about each dQ making up Q. It's going to incrementally build up. So each of those dQs does a little dW for that voltage difference. The voltage difference, the voltage is, that's determined by the battery. Each of those charges is coming in at one at a time, not, you know, it's pretty simultaneous, but just imagine, if you will, one dQ over to this left plate, right plate, and each of those dQs build up to make Q. Each of those individual dQs are doing dW amount of work to make eventually the total amount of work, which is Q delta V. And so from this equation, I'm just gonna expand on that. So that becomes dQ Q over C, because delta V from capacitance is C equals Q over delta V. Well, delta V is Q over C. Then we can find out the total work in the system. So we have dW equals 1 over C 0 to Q. Now, it doesn't matter positive, negative Q, because we're talking about magnitude. Each plate is going to build up to Q, positive or negative. And this integral here becomes Q dQ. Okay, so from this point, so all we're doing is taking a microscopic look at how charge is built up on each plate. Little dQ to do dW over that delta V. What's the total work? Well, integrate both sides. 0 to W, if you will. That becomes work total equals, now when we integrate this Q has an understood 1 here. And so we know by analysis of antiderivative that this is going to be 1 plus 1 divided by 1 plus 1. So it'll be Q squared over 2. So this becomes, if we will, big Q as we have in the integrand there. So this will be Q squared over 2, which is the result of this, times C. So the work done on the entire system for all of the dQs to make Q is going to be given by this expression, Q squared over 2C. So the work required to bring each charge from the battery from the plate that had no charge at first all the way up to Q is this expression. Now we can play around with it just like we did with the equations for power back in classical physics and classical mechanics. Power had 3 expressions. We'll see now that work here has 3 expressions. C, we know, is delta V over Q, or 1 over C is delta V over Q. So this can become equal to Q squared. So we're just playing around with this. So 1 over C is delta V over Q. And then that's delta V over 2Q. There's a 1 over C there. And then work equation becomes 1 1/2 Q delta V. So that's another expression for work when you know charge and voltage. This will be expression for work when you know charge and a capacitance. So again, the amount of work to bring one charge from the battery up to the plate to make big Q, given by at least two expressions here. All right, and then our last, one other equation for work. So 1/2 Q delta V, we know that Q is equal to C times V. So solve for Q is C times delta V, so this becomes 1/2 C delta V. That becomes 1/2 C delta V squared. We can call it work to bring it up, and that's the amount of energy that's in between those plates, the amount of the change in potential energy, because work is equal to delta U. So as we're just looking at the plates as a state, we're looking at the plates at that one moment, we can just, in terms of that perspective, we know that this equation is work, which we can also say is the energy stored in that capacitor. So we have three equations for the energy between the capacitor, which is the same thing as the work required to bring those charges to those plates. So this is static energy, and this is equal to the amount of work done. And we have this equation here, same as this, and this equation up top. This is also U. So just the energy stored in a capacitor. And we've seen how we can derive energy from work in other situations. Change in potential energy, gravitational potential energy system, electric field, those situations. So those are equations for work or energy stored in a capacitor. Okay, let's see if we can do something else to that energy expression. So again, let me write it up here, chopped it off. Energy stored in a capacitor, at least one version. All right. So let's see. We know that delta V is equal to electric field times distance. We're just going to express everything in terms of the electric field that's there. Or substituting expressions for voltage in terms of E times D, just rewriting it a different way. So this is our voltage in terms of electric field and distance. We know that the capacitance between two plates in terms of its area and its distance is epsilon naught A over D, right? And we just substitute those expressions. And we have U equals 1/2 C delta V squared, 1/2 epsilon naught A over D times E squared times D squared, because that's delta V squared. And then, you do your little substitutions there and cross out. So 1/2 epsilon naught E squared A times D. So this right here is you know, that's our energy in terms of those new expressions. So far, so good. We just made a bunch of substitutions. Once we derive this one, we just now playing around. Oh, okay.
Yeah, I got it.
Yeah, so it's like, okay, 1 over C, C is Q over V, okay, 1 over C is delta V over Q, okay, substitute. One last thing with this expression. Okay, since volume is V equals A times D. Now, this is like a physicist playground. Like now you get an expression. So can I express it even further? Oh, I know A times D is volume, and okay, just do all kinds of things here, right? Since volume is V equals A times D, then we can define something called the energy density as energy densities, like, you know, like surface density, linear density, charge density, surface charge density, volume charge density. Now we got something called an energy density. Is energy per volume, right? It's like charge per volume, or charge per area, charge per length. Energy density, in the extreme case here, because we're talking about volume, A times D, energy per volume is volume energy density, or just energy density. Then we can just substitute, right? So we have 1/2 epsilon naught E squared A times D over A times D. And then our energy density, epsilon naught E squared. That's our equation for energy density. Energy density in an electric field is proportional to the square of the electric field. Take the E field, square it, it's UE proportional to electric field square. All right, set enough on that. Let's do a few examples in our time that's left. That was just 26, so we're gonna have to 27. Let's see, do you guys gotta go, or can you stay around a little longer and do some 27? Or
I can stay.
what about you, Jeremy? Next time? You stay today?
What about next time?
Next time?
Yeah, okay, I'm good with it.
Okay, I didn't quite hear him. Okay, let me pause this. Okay.